Hello students, 6.9 is exponential regression. Given the data below, use technology to do the accompanying tasks. So we have this table here that is recording the different years from 2010 through 2020, but not all of those years in between, and the population of some town, we'll say. Part A is perform exponential regression of the form y equals a times b raised to the x. So what we're going to be doing here is using technology to figure out what a and b are so that we have an exponential curve that best fits this data. I'm going to go straight to Desmos, where I already have the data entered into a table. Recall, if you want to create a table, you hit the plus sign and then select table. And if you create multiple tables in one sheet, they will automatically have different subscripts on the x and y. In this here, you can see that I have a total of 3 tables already entered, and they defaulted to having different subscripts. That's so Desmos will know which table to look at when I do my regression formulas. Okay, so in this next space here, I'm going to enter the formula for an exponential curve. Now normally that formula would be y equals a times b to the x, but we want to refer to the data in this table. So use y1, so y and a 1, and then do the tilde instead of an equal sign. And the tilde can be found at the bottom of this keyboard here. This tells Desmos you're doing regression. And then we have a times b raised to the, and if you just say x, it won't do anything. You have to say x1 so that it knows to refer to this table here. All right, so here is our data, and we wanted to find a exponential curve that best fit the data. And according to this calculation, and you should also make sure there's a couple ways to do exponential regression. If you want to do it in the way that will be accepted by the homework when you're doing this online, make sure you check this little box called log mode. This uses a technique for doing the exponential regression that is compatible with your online homework and the answers it will accept. So now we have what a and b are. I'm going to insert a few lines here. So I'm going to say plus and type in, go to expression, and let's add another one. So the a is extremely small, you'll notice. It's 1.2746 times 10 to the negative 19. So it's like moving the decimal to the left many places. If you want to see more digits of a, though, then you can simply just type in the letter a here, and you'll see a few more digits. So 1.2745895076 times 10 to the negative 19. Same thing for b. If you need to see more digits, then type in b here, and you'll see more digits of b. So part A was that we had y is equal to ab to the x, where a is approximately 1.2746 times 10 to the negative 19, and b is approximately, just remember, times 10 to the negative 19, just make sure we understand what that is. If I had 63 times 10 to the negative 4, what this means is you find the decimal and then you go left 4. So it's really 0.0063 is what 63 times 10 to the minus 4 is. That's called scientific notation. And when Desmos has extremely small or extremely large numbers, it uses scientific notation. And b was approximately 1.02667. Now let's do part B. Part B is to perform exponential regression of the form y equals p naught times e to the kx. Now the only thing that's really different here is that instead of doing a base b to the x, we're doing the base e raised to a number times x. The p naught and the a have the same position. In fact, you could just use a times e to the kx. It really doesn't matter what letters you put here. In this case here, you could have done c and d, whatever. I'm just showing you a variety of different parameters. So we have p sub 0, or p naught, times e to the kx. I'm going to type that in exactly using the p naught and the k. Let's go back to here. I'm going to insert another expression, a place to put this. Let me move that up here next to the other one. And we want to refer to the first table, so make sure you use y sub 1. Y sub 1, tilde, p naught, so I'm going to do capital P. There it is, a sub b. See that a sub b? And then put a 0 there. So there's the p naught, and then arrow over. P naught times e to the exponent, and then k times x1. Make sure you do x1, and it makes that subscript. All right, so this gives us a regression model. Let's put b here. Now we're doing y equals p naught e to the kt, where p naught is approximately, we'll write that down in a moment, and k is approximately. And notice the p naught is the same thing as we got for the a before. So it's also 1.274 roughly times 10 to the negative 19. 0.026. Okay, now these two models, the only difference really between the two models is the exponential part. And this is b to the x, this one's e to the kx. I should have put an x there, not a t. The role of the coefficient a is the same role as this coefficient p naught. So it's not surprising that we get the exact same number here. Now the b and the k are different, but part c of this is to show that these two models are in fact the same. In order to do that, we simply have to, if you take this model here, you can effectively think of e to the kx as e to the k and then raised to the x. So to show that these two models are the same, we just have to show that e to the k and b are the same thing. The p naught and the a are already the same thing. We've got to show that the b and the e to the k. Let's put it here, part C. We need to show that b is equal to e to the k to show that these models are in fact the same. Let me insert another line here, an expression, and let's just say, what is e raised to the k? So e raised to the k, and it's going to refer to the k that's already been used. And notice, compare e to the k and b, and they are in fact the same. So we already knew that b was approximately 1.02667, and we've used technology to show that e to the k is also approximately 1.02667. So this is enough to show that these two models are in fact the same. It's just two different ways to go about creating a exponential regression model. Now part D is to use the model to predict the population in 2025. Okay, so we have two different models here. One is green and one is red. If I hide the red one, you can see that the graphs even look alike, another confirmation that we are in fact looking at the same curve. Doesn't really matter which one I use. Let's go ahead and just keep the first one. So I'm going to X out this second one and just keep the first one and reveal it. I don't need this e to the k, I don't need this, and I don't need that any longer. And now we want to use this model to make some predictions. One prediction is, what is the population predicted to be in 2025? So I'm going to type in a vertical line, x equals 2025, and see where our curve intersects this vertical line. And we can see that at this year, we expect the population to be around 17,927.7. So 17,927.7. And let's say we're using y for the population. We said the year was x and the population was y. So we're going to say when x is equal to 2025, then we got y is approximately equal to 17,927.7. And we never said what this is population of. Let's just say it's a population of people, so I have something to write here. And then part E is to use the model to predict when the population will be 20,000. So for that, we just got to do a horizontal line. Let me add an expression, put a horizontal line in here, y equals, and we want it to be 20,000. Okay, let me hide the vertical line. We don't need that. And the horizontal line intersects the model, the curve, at an x-coordinate of 29.156. We said y was 20,000, and then we got that x was about the year 2029.156. And of course, we could convert this part here to try to predict what part of the year we're actually in, which month are we in, what day are we on, etc. We're not going to spend the time to do that. I leave that to you to determine on your own. Okay, and that answers all 5 parts of this. And then we're going to repeat this now for the next example. Given the data below, use technology to do the accompanying tasks, perform exponential regressions. These are all the same first 3 questions, but just different data now. So again, let's say x will be the time measured in hours, and y is the drug in grams. So it looks like, notice the drug is going down. So this is maybe drug being metabolized by a body. It's been maybe injected at time 0, and then at different number of hours, we detected a decreasing amount of drug in the system. So it looks like an exponential decay model will be appropriate. Now that will automatically come out by giving us the correct B or K, whatever the case may be, when I do my regression models. Okay, back to here. Let me go ahead and just delete everything that related to the last problem. Get rid of that. Oops, I deleted the wrong thing. Let me undo that. Put that table back. Delete this and delete the first table. That's gone. Let me click the home button to go back to our normal scale. And then I already have the data entered here for our next problem. Reveal the data, and now let's go hunting for it. Looks like I just need to bring the y-axis down to see this data. So here's our data, and we can see that as time goes on, we do in fact see decreasing amount of drug, so we expect an exponential decay model. And let's insert an expression. Let's put that below the table, not that that matters, and type in y sub 2, so just y2. The nice thing about Desmos is when you do a variable and then a number, it automatically makes it a subscript, so you don't have to go to the subscript symbol. Tilde, we do have to go tilde. A times B raised to the x1. Notice nothing happened. That's because I should have typed in x2. Because our table now, the headers are x2, y2, so be careful about that. Make sure the variables you use match the headers of your table. And also make sure you're in log mode, so click that log mode button. Okay, so this gives us the A and the B that we are after. So for part A here, we did y equals A times B to the x, where A is approximately and B is approximately. A is approximately 28.3613, and B is 0.78976. Make sure when you're doing this online that you enter the correct number of digits that it wants you to round to. And if it wants you to round to more digits again than you can see here, then just put another line of expression here and just put the letter B, and you'll see B but with more digits. The fact that B is less than 1 is the reason why it's a decaying exponential. Right, when your base is less than 1, you'll have a decaying exponential. So that's what we didn't have to adjust. We just had to type in A times B to the x2, and automatically it gave us a decaying exponential because the data was decreasing. And so B is less than 1. Okay, for part B, we're going to do a model of the form. So here we go. P naught e to the k x, where P naught is equal to, now you can predict what P naught's going to be. We expect P naught to be the same as A, so I expect it to be 28.3613 again. And, sorry, that shouldn't be a B, that should be a K. And knowing that the relationship, we know that when I do part C I'll have to show that B is the same thing as e to the k. So if I already know B, then I should be able to predict what k is. Right? It should be that k is equal to the natural log of B. Just convert this B equals e to the k to exponential form. And so I could predict k right now by doing the natural log of B, but we're going to do that we'll do that in a moment. We'll do it both ways. Just keep that in mind. Let me get rid of this. Keep that in mind as we type in a new regression model. So let's insert an expression. We move this down here and type in y sub 2 tilde. Let's go ahead and B. Just call it the P naught, be all official. Got that subscript, P sub 0 times E raised to the K times X2. And then make sure you click log mode. So this gives us the same P naught that we had, that A was. Notice they're the same, P naught and A. And it gives us a K is negative 0.236, we'll say. Negative 0.236, okay. So there's our model using a different form for the exponential regression. Now we need to show that they're the same. We could show that they're the same by showing that either one of these two statements is true. All right, we've already shown that, let's show that this bottom one is true. So we already know that K is approximately negative 0.236. Now let's do the natural log of B and show you what that is, see if they're the same. So I'm going to insert an expression and just do the natural log ln of B. And notice we get the same, ln of B and K are the same. Let's see, where's K hiding? Oh, K is right above it. ln of B and K. So this is enough to show that the two models are the same. So check, let's put little checks there to indicate that, or just put a check there that that's the same thing as K. And now let's do part D. Use the model to predict the amount of drug at 6 hours. So I'm going to do a vertical line, add an expression. Vertical line, x equals 6. See where it intersects. Let me see, when x is 6, y is about 6.882. So x is 6 hours, and y is about 6.882, and this was in grams of drug. Make that look a little bit better. And then part E, use the model to predict when the amount of drug will be 5 grams. So now I want to make this, do a horizontal line here instead of a vertical, 5, and make that be y equals instead of x equals to make a horizontal line. Change our scale so we can see where they cross. And they cross right there. So when y is 5 grams, we expect x to be about 7.353. So y was equal to 5 grams. We got x was about 7.353 hours. Okay, one more slide. Now we're going to do a logistic regression. Perform logistic regression of the form, and the form is given right here. This is your basic logistic model. It's a constant over 1 plus a constant times e to the negative constant times x. And then use the model to predict the number of bacteria at 7:30 a.m. Use the model to predict when there will be a 1400 bacteria, and use the model to predict the maximum number of bacteria. So in this case here, x is the number of minutes that have elapsed since 7 a.m., and y will be the amount of bacteria measured in hundreds. So when we say 5.5, that really means 5.500. In other words, 5,500. No, sorry, 5.5 hundreds means 550. This would be 1,000 bacteria, or that would be 1,000 bacteria. This would be 1,200 bacteria. This would be 1,250 bacteria. And this is the number of minutes since 7 a.m. Okay, so first let's just do our model. Let's get this out of the way. I'm going to go back to Desmos. Let's get rid of all the stuff I don't need for this, which is the second table gone. And let's delete that model, delete that, delete that. So here we go. We're down to just this last table, x sub 3 and y sub 3. Feel free to change the subscripts now back to 1 and 1 if you want, and use x1, y1. It doesn't matter. So here's our data. Let me change our scale. Let me hit the home button and zoom out a little bit and zoom this way. You can sort of see a logistic curve, right? A logistic curve is a curve that will flatten back out and follow an asymptote. Let's model this with logistic. So we type in y sub 3, because that's what the table is, y sub 3, tilde, and then a divided by, and it was 1 plus b times e raised to the negative k x, and then put x sub 1 to refer to the table. Oops, I meant to say x sub 3. I was like, why don't we see anything? X sub 3, of course. Our table is x sub 3. There we go. Here's our logistic curve that passes through the data. All right, so for part A, we have y is equal to a over 1 plus b e to the negative kx. You could have left the negative off this model, and then k would have turned out to be negative for us. But because I have the negative typed in, then the k turns out to be positive. So we'll have to write in what a is, what b is, and what k is. All right, so a turned out to be about 15.4884. Notice the little box, the check that says log form, there's no box there, because for doing the logistic best fit curve, there's just one way that Desmos is doing it, and that's also the way that your online homework will accept the answer. For part, let's see, number B was 1.939, we'll say. 1.939, and then the K turned out to be 0.1643, we'll say. 0.1643. So I did a little bit of rounding here, but good enough. Just make sure you round to the correct precision as demanded by your homework when you do this. Okay, part B. Use the model to predict the number of bacteria at 7:30. So at 7:30 a.m., that is how many minutes since 7 a.m. So we have to convert this to an x coordinate. So I need to use x equals 30, because it's 30 minutes since 7 a.m. So we'll use x equals 30, and then use the model to give us what y would be. So I'm going to do a vertical line, x equals 30, and see where they intersect. and 15.27 approximately. Remember, this is in hundreds of bacteria, so that means really 1,527 bacteria is the predicted amount at 7:30. Part C, use the model to predict when there will be 1,400 bacteria. Okay, so let's make a horizontal line. Y equals, and make this, so if you type in 1,400, that's going to be off our scale. Remember, 1,400 bacteria mean that we really want Y just to be 14, because the Y coordinates are measured in hundreds of bacteria. Okay, so we know that 1,400 bacteria means that Y should just be 14, and then we found out that X was approximately 17.668, meaning that the time is approximately 17.668, I'll just write it this way, minutes after 7 a.m. So it's going to be somewhere between 7:17 and 7:18 as far as time is concerned. And you would want to, if you want to figure out how many seconds in between, you'd convert 0.668 minutes into seconds to determine how many seconds that is. I'll leave that to you to determine, though. Part C, use the model to predict the maximum number of bacteria. Now, the maximum number of bacteria, this model, all logistic curves level off. The question is, how high? Let's create a window that lets me go up to 20. Right. How high is the ceiling of this logistic curve? Where exactly is the horizontal asymptote? And that can be given by the numerator of the logistic model. The logistic model has a numerator of A. So if I just type in Y equals A, that'll give me the exact location of the asymptote for this model. So this model predicts that this environment where the bacteria is in, maybe in a petri dish or something, or on a piece of fruit, there's only so much bacteria that can survive in this environment, and according to this model, that maximum number of bacteria is 15.8488. Let me make that approximate. That's going to be that horizontal line. That is the max of our logistic model. So that means a max of 1,548.8 bacteria. Okay, and that is how we do a logistic regression when our data supports the idea that there would be a maximum carrying capacity for any certain population. And that wraps up exponential regression.